welcome you all in this presentation related to the subject materials processing fundamentals and practical, and we will be talking about the few more fundamentals related to the welding of metals. In this particular presentation, we will be talking about the various factors that affect the weld joint performance, common heat sources, effect of the power density on the heat input and the weld joint performance, and what is the need to protect the weld pool from the atmospheric gases. Okay. So, let us see, the heat for development of the weld joints can be generated using the various means. Okay. So, say heat is being delivered for fusion welding, we are melting the fank surfaces of the base metal using the suitable heat source. So, this zone is brought to the molten condition. Okay. Okay. Now, in autogeneous welding, this is just the molten metal being created by melting the parent metals. But in case of, if we use filler, then filler metal has to be fed, and then the filler metal is mixed with the molten base metal. Okay. So, depending upon the condition, whether filler is used or there is no filler, this is one. Second is that how, when the heat is supplied, how the zone next to the weld metal is getting affected with the application of the heat. So, the changes being experienced by the underlying base metal next to the weld zone, that is heat affected zone. Okay. When the things are brought to the molten state, then the molten metal will tend to react with the gases which are present in the atmospheric gases which are present in the arc zone. So, these gases will tend to form their oxides and nitrides. So, when all these things, considering this scenario, okay, so if we have to see that how much is the heat affected zone being formed, how much the oxides and nitrides are being formed, and what is the size of the weld zone, whether it is very small or very wide, and how the property variation across the weld joint is taking place. So, depending upon the choice of the filler metal or no filler metal, we may have the distribution of variety of distributions like this. So, our heat affected zone is soft, you can say HAZ is soft for this distribution, weld is matching. Our weld can be harder, while the heat affected zone can be softer if we choose the suitable filler which is strong. Alternatively, our heat affected zone will always be there, but weld zone can be weak, and then heat affected zone can also be weak. Okay. So, this is again the HZ softening, but this kind of scenario with regard to the hardest distribution across the weld joint will be happening only when we use the under matching filler. Okay. If we use over matching, then we will be getting significant increased hardness and strength of the weld zone. Okay. This is the over matching and under matching. Certain transformation hardening metals, what they show, like the hardness of HZ is high and the weld is certainly high. So, there is no drop in the hardness of the. So, here we can see this is the HZ, this is the weld zone, and the both HZ and weld zone are harder and stronger than the corresponding base metal. But this is typically observed in case of the transformation hardening metals. Now, in this scenario, we will try to see that what are the various factors that will be determining the performance. So, certainly the one aspect is soundness, means the free from defects, free from defects. If there are defects, then certainly the joint performance will be compromised. These defects can be in form of porosity or in form of inclusions, cracks, etc. Okay. So, if you have unfavorable welding conditions, then these defects will be there. Okay. The second thing, either heat input has been supplied too much, leading to the very wide heat affected zone and significant thermal, significant degradation of the parent metal properties. So, that will be leading either to excessive softening or excessive hardening, and both may be undesirable. Okay. So, these are the things that will be happening in totality, the weld zone and heat affected zone. These are the two main things that we have to consider. Okay. So, as far as the performance of the weld joint is concerned, first thing is the soundness. The joint must be free from any defect, and these are the two main aspects. How this, what is the microstructure of the weld metal based on the composition, and based on the cooling conditions being experienced, and if everything is fine, then the joint will be sound. Otherwise, there will be defect in the weld metal in form of porosity, in form of inclusions, in form of cracks. Okay. So, this is one aspect, how the weld metal and heat affected zone, what is the microstructure and mechanical property of the weld metal and heat affected zone, that is one, and how good weld joint is being made so that it is free from the defect. If a joint is being made having the defects, then certainly its performance will be lesser due to the two reasons: due to the reduced load resisting cross sectional area. Wherever there is a defect, there will be like either air or there will be non-metallic materials which will not be supporting the external loads. So, that in turn will be leading to the reduced load resisting cross sectional area. Okay. Microstructure will of the weld metal and heat affected zone certainly be affecting the mechanical properties, either in form of the hardening or softening or with the matching properties. So, it is important to consider both weld and heat affected zone microstructure and mechanical property. Okay. Lot of metallurgical changes take place in not just in the weld zone, but also in the heat affected zone. Okay. So, these microstructural changes, microstructural changes govern the mechanical properties, corrosion resistance of the weld joint significantly. That is why the mechanical metallurgy of the weld joint, which is happening in the weld metal or also in the heat affected zone, that is very important. Okay. And for a given microstructure, we will get one set of properties, and if due to the controlled heating, cooling, post weld heat treatment, if the microstructure is altered suitably, favorably, then our mechanical performance will be enhanced accordingly. Okay. In addition to these aspects, we may have the desired microstructure, desired mechanical properties, but if we have residual stresses developed in the weld joint, then that will be leading to the increased distortion tendency and the reduced mechanical performance in terms of the reduced tensile load, in reduced the fatigue performance. Okay. So, we want to minimize the residual stresses, we have to realize the desired set of mechanical properties by adjusting the microstructure suitably, and for that we need to control the weld structure and the composition, weld structure of the structure and composition of the weld metal and the structure of the heat affected zone, because composition of the HZ cannot be adjusted, and also we need to make all the efforts so that our the joint is sound. Okay. So, the performance of weld joint in any case is governed by the two main aspects. One is the weld metal, okay, whether it is free from the defects, it is having the desired microstructure, or the heat affected zone. Okay. What kind of the microstructure is there in the heat affected zone, and what are the metallurgical transformations which are taking place. Both these factors in turn will be governing the mechanical performance of the weld joint, and depending on the composition and the kind of the heat input that has been there, that will be determining the residual stresses. Okay. So, that is about the major factors and their effect on the performance of the joint. Okay. So, in case of the if we are using autogeneous welding, then it is the heat input only that will be controlling the microstructure and mechanical properties. Okay, because that will be affecting the weld thermal cycle. But if we are using the filler metal, then the composition of the filler metal apart from the weld thermal cycle will also be playing significant role. So, when you use filler metal, it gives us liberty to choose the filler metal as per our need. Okay. But when we use the autogeneous welding, when the filler metal is not used, then it is the heat input that controls the microstructure and mechanical properties. Okay. That is one aspect. So, the microstructure and mechanical properties of the weld metal in case of the in case when the filler metal is being used, then that will be determining the composition and the microstructure and mechanical properties of the weld metal significantly. But the microstructure and mechanical properties of the heat affected zone is primarily governed by the weld thermal cycle, which is significantly affected by the net heat input or the preheating if it is there, thermal conductivity of the base metal and the section thickness. So, these are the various factors that will be determining the kind of the thermal cycle that will be experienced by the base metal in the heat affected zone, and that in turn will be governing the microstructure and mechanical properties of the heat affected zone. Okay. So, as far as the weld metal is concerned, as I have said, the composition of the weld metal, if we use suitable filler, then that we can adjust accordingly, but in autogeneous welding we need to just melting the fixed surfaces. Okay. So, the weld metal significantly govern the mechanical properties and the corrosion performance. Okay. Why? Because weld metal composition can be adjusted by using the suitable filler metal in order to realize the desired corrosion resistance and desired mechanical properties. In addition to this, the heat input or the weld thermal cycle being imposed for the welding, that will be determining the microstructure and mechanical properties of the weld metal. And in this, at the same time, if we do the proper protection to the weld metal, then it will be use of the suitable weld thermal cycle, use of the suitable welding procedure, then that will help us in developing the sound weld joint. So, if we forget for a while that there is a heat effector zone, if we are having just the weld zone, okay, then the performance of this joint will be dictated by what? The composition of the weld metal, because it is determining the microstructure. Then the kind of the microstructure being developed, that will be influenced by the weld thermal cycle being imposed, and if it is free from the defect, then that will depend on the how good protection is being provided. If there are defects, then certainly the weld metal performance will be reduced. Okay. So, for enhanced soundness, we need to provide the suitable protection to the weld metal, and for realizing the desired microstructure, we have to have suitable composition, and we have to impose the suitable weld thermal cycle through the control of the heat input. So, major thing here is the mechanical and corrosion performance of the weld metal is significantly dictated by the kind of protection being provided to the weld pool and the kind of heat input being given. Okay. So, how much heat is being given, that is a very important aspect here, like say, okay, like so these are the two components to be welded, and say, so we need to supply the heat, okay, using the suitable heat source. Now, heat source can be in form of flame in case of the gas welding, it can be in form of arc in case of the all arc welding processes, or it can be in form of the laser beam for laser welding, or electron beam in case of the electron beam welding. Okay. So, these are the different kind of the sources of the heat. Okay. But each heat source comes with the unique power density, means how much power in form of the heat is being delivered per unit area, okay, watt per mm square. Higher the power density means the lot of heat is being delivered over a smaller area in shorter time, in very less time. Okay. So, if we see this, the gas welding power density associated with the gas welding is very less, like say 100 to 1000 watt per centimeter square. For arc welding, it is in like say 10,000 to the like say 10 to the power 6 watt per centimeter square. So, there is a very wide range. Okay. Then we have electron beam welding and the laser welding. So, if we see from gas welding to the arc and to the radiation, there is a continuous increase in power density, which means if we use high power density heat source, then in very less time we can deliver the desired heat for realizing the melting. So, since the heat required for melting is a physical property which is constant. So, we supply the heat and give desired heat is supplied, so that it is brought to the molten state. When we use the low power density, it takes lot of time to deliver the desired amount of heat to bring the fin surfaces to the molten condition. Okay. And in that process, we need to supply lot of heat. So, say this is an example, the time for melting increases significantly when we work with the low power density welding process like arc or like gas welding heat source. But when we work with the high power density process like the laser or electron beam, okay, then high power density means the desired amount of the heat needed for the melting the feng surfaces can be supplied in very less time, and therefore the feng surface melts quickly, and therefore the amount of heat that we, so the time required for melting is very less, and when the time required to melt is very less means things are melted very quickly and heat source can be moved ahead. So, the total amount of heat to be supplied for melting the feng surfaces when using the high power density welding process is very less, and when we are using the low power density heat source, then time required for melting is too much, and therefore we need to supply lot of heat because it takes a lot of time, and when we are supplying the heat, you see heat is being supplied. So, if it is taking longer time means lot of heat due to the thermal conductivity of the metal will be dissipating to the underlying base metal, and therefore, you require lot of heat input, very high heat input for realizing the molten condition, and therefore, you see considering this, so power density, so our heat input trend is coming down with the more heat when we are using the lower power density and less heat when we are using the high power density, and this is what we can see. When we are using the low power density heat source like gas welding, net heat input required is very high, that is what we can see in kilojoule per mm, while when we are using the arc it requires further lesser little higher power density. So, it requires somewhat lesser heat input, and with the laser welding or electron beam welding, when the power density is very high, heat input required is very less. Okay. So, means using the laser and electron beam with very less heat, we can realize the melting of the feng surfaces for development of the joint, while in case of the gas welding and arc welding, as comparatively we need much higher heat input for realizing the melting of feng surfaces. So, this is what we can see easily from this slide, that the different welding processes offer the different power densities, and the power density directly affects the net heat to be supplied for melting the feng surfaces for development of the joint. Higher the power density, lesser the heat input, lower the power density of heat source, higher the heat input that is desired. Okay. As I have said, when we realize the melting of feng surfaces, okay, especially under the ambient conditions, so the oxygen and nitrogen will be reacting with the molten metal. So, this can happen in multiple ways. One, things are getting dissolved. So, as per the solubility, gases are more soluble in liquid state, so they will getting dissolved. Okay. Because of the rapid cooling rate, these gases are not able to come out, so that will be leading to the development of defects in form of porosity. Additionally, they react chemically. Okay. So, the chemical reaction of the oxygen and nitrogen with the metal will be leading to the formation of oxides and nitrides. So, that in turn will be leading to the development of the defects. Okay. So, if the weld joint is having porosity or inclusions, then this certainly will be reducing the load resisting cross sectional area of the weld joint, and that in turn will be degrading the mechanical performance in terms of the reduced tensile load carrying capacity or reduced fatigue resistance. Okay. If we see the different processes offer the different kind of the protection to the weld metal. For example, if we see here the submerged arc welding, this offers very high oxygen content in the weld metal and lesser nitrogen content. A shielded metal arc welding or manual metal arc welding or stick electrode welding, there or manual metal arc welding, there are multiple names. This offers higher oxygen and higher nitrogen content in the weld metal. Self shielded arc welding like flux core arc welding, this offers the higher nitrogen and reasonably higher oxygen content in the weld metal. The cleanest weld metal is produced by the TIG. Here you can see the TIG offers the minimum oxygen and minimum nitrogen content in the weld metal. Okay, and the MIG or the MAG welding that offers a little higher oxygen and lesser nitrogen content. So the MIG is the next cleanest, second best clean welding process of with regard to the oxygen and nitrogen content in the weld metal. So if we have the lesser oxygen and nitrogen content, it will reduce the tendency of formation of porosity, it will reduce the tendency of formation of inclusions. So we will be producing the more sound weld, okay, which is free from defects. Why there is a difference in the protection, why there is a difference in the oxygen and nitrogen content in the weld metal produced by the different processes. So if we see, the molten flux approach is used in case of the, because we use most of the oxide fluxes. So these molten fluxes in case of the submerged arc welding offers the higher oxygen content in the weld metal. So molten flux is used in case of the submerged arc welding and also in case of the shielded metal arc welding. So therefore we get the higher oxygen content. Inactive gases are used in a mag welding or also in SMAW process, both, and therefore we have in SMAW the protection is very weak because the inactive gases are produced by thermal decomposition of the flux. Like say this is the core wire, here we have the coating and arc is there between the base metal. So here the coating thermally decomposed by the heat of the arc to produce the inactive shielding gas around the arc like this. Okay. So, the protection is very limited and it is not very effective, and therefore, what we get higher oxygen content and nitrogen content in case of the SMAW. Inert gases are used in case of the MIG welding or the TIG welding processes, and therefore, we have very lesser oxygen and the nitrogen content in the weld metal because it provides very effective the protection against the weld metal. And the inert gases are also used in the laser welding, but in case of the electron beam welding we use the vacuum mostly, okay, for realizing the high quality weld. So as far as the arc welding is concerned, the GTAW or the TIG welding process offers the cleanest weld. Okay, these are the various approaches for developing the sound weld joint by providing the protection, and so the different types of the protection is used during the welding by the different processes. Now we'll see how the heat is generated when we deal, what are the different approaches of heat generation for the welding. So the first is the gas welding, where the chemical reactions are used. So say fuel gas and oxygen mixture, okay, oxygen mixture is burned. So fuel gas, say acetylene, is burned with the oxygen to produce the CO, hydrogen and the heat, okay, and then this CO further reacts with the hydrogen and oxygen to form the CO2 and H2O, and the heat is generated. A typical flame structure which is produced, say this is the torch tip, okay. So there is an inner cone that is produced and there is an outer cone. These are the two cones which are usually produced. So we have outer cone and one inner cone. Inner cone produces the lesser heat while the outer cone produces the more heat. Okay, that is what we can see. Outer cone produces the more heat, that is 812 kilojoule per mole, while the inner cone produces the lesser heat 448 kilojoule per mole. But if we see, the temperature of the outer cone is lesser than the inner cone. So, how can we explain this? Inner cone temperature is 3100 degrees centigrade, while the heat generated is just 448. On the other hand, outer cone temperature is the lesser, that is 1275 degrees centigrade, while the heat generated is more. Okay, so to explain this, we have just one simple explanation, that outer cone is exposed to the ambient conditions, that is at 24 degrees centigrade. So there is a very rapid heat loss from this large surface area of the outer cone, and therefore maximum temperature attained in outer cone is lesser. Okay. On the other hand, inner cone is of the shorter, the surface area of the inner cone is less, that is one. Second, it is surrounded by the already hot outer cone. So, the heat dissipation from the inner cone to the outer cone is limited. So, the smaller surface area and surrounded by the hot outer cone. So, these are the two main reasons behind the higher peak temperature of the inner cone despite of generating the lesser heat input. Okay. So, this is about the gas welding thing. Of course, for the welding purpose, we try to keep the torch at a distance from the base metal surface in such a way that the surface of the base metal is in the inner cone zone. Okay. So, that the heat the inner cone is exposed to the surface of the base metal for the welding purpose, so that the melting can be realized fast. Different fuel gases generate the different amount of heat and different peak temperatures. That is what we can see here. Acetylene in primary zone generates the 19 units of the heat. In secondary zone, it generates the more amount of heat, that is 36 unit. Total heat generated is 55 and peak temperature generated is 3100 degree centigrade. While that for propane it is 88, much higher, but lower peak temperature. For hydrogen it is 2390 degree centigrade, and for natural gas it is 2350 degree centigrade. So, since the maximum peak temperature is offered by the acetylene, this helps in melting the parent metal very fast and realizing the welding at a higher speed. Thermite welding is another chemical reaction based process where mixture of the metallic oxides are used, metallic oxides and the metals like aluminum. Okay. So, the metallic oxides like iron oxide and the aluminum, when these are allowed to react, it produces the lot of heat by exothermic reaction, produces the alumina and the molten iron. Similarly, for the welding of the copper, like copper oxides plus aluminum is used. So, this again will be producing the heat through the exothermic reaction, producing the alumina and the molten copper. So, oxides of the iron, manganese, copper, chromium are used with the reactive metals like aluminum and magnesium to produce the heat by exothermic reactions and facilitate the development of the molten metal. Then this molten metal is actually fed. Say this is where the reaction is taking place, then the molten metal is produced and this is fed in the gap between the two components to be joined. So, once this is filled in, here the solidification will be taking place. That is why this is known as cast weld process. Electrical resistance heating, this is very based on the simple principle, like in resistance spot welding and resistance welding process. Here we with the help of suitable electrodes we supply the current, and then the current passes through the joint intersection through the interface. So, I current I square R T heating, the current is allowed to flow for time T. R is the contact resistance at the interface, and I is the current which is being used for generating the heat. So, this is called basically Joule heating, where I square T heating principle is used, where I is the welding current, R is the contact resistance and the T is the time for which current is allowed to flow. Okay. So, that is how the heat is generated in case of the resistance welding process. In case of the friction welding, where one component is fixed and another is moved, say this can be linear motion or reciprocating motion. So, what is done, heat generation rate in case of the friction under friction condition is governed by like the fraction of the energy eta. F is the friction force and the V is the velocity, relative velocity. So, where is the fraction of the energy that is converted into the heat, which can vary from say 50, 60, 70%. F is the total, F is the friction force obtained from the product of the normal force and the friction coefficient, and V is the relative velocity. So, F is equal to mu n. Okay. N is the normal force that is being used. So, although during the welding heat can also be generated by the plastic deformation. So, in friction welding conditions, like say when the two surfaces are rubbing each other under the normal load, okay, either under in the linear manner or this is fixed, this is moving. So, either linear or the rotary motion. So, some kind of the interfacial plastic deformation is also involved. So, not just the frictional heat is generated, but the heat due to the plastic deformation is also generated. depending upon the kind of the relative velocity, normal force, etc. So that also contributes in generating the heat. Why the heat input is important in determining the joint performance? So if we have to see this, because when the heat input is high, cooling rate experienced by the weld zone is inversely proportional to the heat input. Okay, this is one thing. So higher the heat input, lesser will be the cooling rate, lesser is the cooling rate, coarser is the grain structure, and coarser is the grain structure, lower is the mechanical property, like this. This is how it goes in. So the kind of cooling rate for a given heat input again will depend upon the like thermal conductivity or the section thickness of the material. So the weld performance depending on the heat input and the physical properties will be getting one set of the cooling rate, and the cooling rate, since the heat input directly affects the cooling rate. So the cooling rate in turn affects the time a weld metal will take to solidify. So solidification rate and the solid state transformation and residual stresses. So as I have said, if the cooling rate is low, then solidification time is long. Okay, that in turn will be leading to the coarse grain structure and reduced mechanical properties. Okay, so the solidification rate, when the solidification rate is less, solidification time is long due to the low cooling rate, then that will affect the grain size, means the low cooling rate means the coarser grain size. It will increase the inclusion and gas entrapment, and it will affect the inclusion and gas entrapment tendency. How? Let us see this. Like say this is the weld zone having the inclusions or the gases. If the solidification time is long, then these inclusions and the gas pockets will be able to move up to the surface, leading to the reduced gas entrapment and inclusion tendency, reduced inclusion and gas entrapment tendency for the longer solidification time. Okay. But longer solidification time will be leading to the coarse grain structure, that in turn will be reducing the reduced mechanical, that will be leading to the reduced mechanical properties. Alloy segregation tendency is enhanced especially when the solidification time is long. Why? Because like say this is the weld zone and we are different alloying elements. If the solidification time is very short, then everything will get free, will be frozen wherever whatever is present, and it will not get time to get segregated. Okay. So, the segregation tendency is minimized when the cooling rate is high, solidification time is less. So, the heat input therefore is important because it affects the chemical heterogeneity or chemical homogeneity, it affects the mechanical properties, it affects the soundness of the weld joint, and it affects the microstructure of the weld joints. Therefore, heat input is very crucial. Okay. So, if we are using a process which is offering higher heat input, means the longer solidification time due to the reduced cooling rate in turn will be leading to the coarser grain structure, reduced inclusion and gas entrapment tendency, reduced mechanical properties, and increased alloy segregation tendency. On the other hand, if you are using the low heat input process like laser welding or electron beam welding, then our heat input will be reduced, solidification time will be reduced, cooling rate will be increased, that will in turn will be leading to the fine grain size, increased inclusion and gas entrapment tendency, improved mechanical properties, and reduced alloy segregation tendency. So, now here I will summarize this presentation. In this presentation basically I have talked about the importance of the heat input, what are the common heat sources used for the fusion welding, and how the heat input affects the weld joint performance. Thank you for your attention.